Hi there, in this video we're going to ask the question, if we were to differentiate a function in time, what would happen to that function in the frequency domain? Okay, so if we were to write down the inverse transform, so we write f of t equals 1 upon 2 pi, the integral from minus infinity to infinity of some function f of j omega e to the j omega t by d omega. Okay, so that's the inverse transform. Now what we're going to do is we're going to differentiate in the time domain, so we'll go d by dt of this function here, f of t. So we're going to differentiate that function f of t. Now if we differentiate on this side, we have to differentiate this side, so that's just a constant. Okay, now the only thing in here that's a function of time is the e to the j omega t. Okay, so well, we can differentiate e to j omega t, we just get j omega e to j omega t, so you'll still be left with integral from minus infinity to infinity of, now you have j omega, okay, and the f of j omega is not a function of time, so that just remains the same. Okay, and you've still got your e to the j omega t, okay, by d omega. Okay, so what we're left with this here then is we're saying if we have some function of time that's been differentiated, okay, then when we find the Fourier transform of it, well, we're just left with a value j omega times, well, this end here has been Fourier transformed, so that's still the same, 1 upon 2 pi the integral minus infinity e to the j omega t by d omega, which just gives us a value f of j omega from our f of t. Okay, so that's just f of j omega. Okay, so that there is the first little transform pair we're going to look at. So it says if we differentiate a function of time in the frequency domain, it's equivalent to taking the function and multiplying it by omega and also multiplying it by j. Okay, so omega is going to scale it by the axis omega, and j is going to rotate it through 90 degrees by a factor of j. Okay, so if we were to then look at d to the power of n dt, so that's the nth derivative of a function of time, then the Fourier transform, what we're going to do is just differentiate again and again, so you would have j omega squared, cubed, so on, so on. So you would have j omega to the power of n of f of j omega. So that's another little transform there. Okay. Now we could go into and do it the other way around about. You could look at what happens whenever you differentiate a function in the frequency domain, what happens in the time domain. So you're going to then say, we're going to say d by d omega, okay, I'll just raise it to the power of n, okay, so this is the nth derivative of the function in the frequency domain, okay, so that's f of j omega. Now in the time domain, well, we're just going to get something that's similar to here, so and this in the time domain goes to the frequency domain, so we're going to end up with, because the equation is we're just multiplying through the same equation, so the only difference is there's no 1 upon 2 pi, and the exponential here is raised to a power of negative j omega t. Okay, so we're just going to end up with our function of time, and we're going to have something raised to the power of n. Okay, so it's going to be a function of time raised to the power of n. Okay, and it's going to be our j function of time raised to the power of n, and it's going to be a negative. Okay, and it's going to be negative because of the the negative value that would be introduced here whenever we use the forward transform as opposed to the inverse transform. So you end up with your negative j t here. Okay, so that there is another transform pair that we can use. Okay, so now for a little example, we'll just quickly go through. If I had a function, let's say we take a triangular wave. That's a triangular wave there, and we say that's time, that's some function of time. Now whenever we differentiate it, so we're looking at d by dt of that, and you can see that when we differentiate that, we're going to have, well, we're going to have the positive rate of change. Okay, so it's going to, the rate of change is going to be up here, and it's a continual positive rate of change, so a particular value, and then we're going to have a negative rate of change, but it's a continuous negative rate of change. Okay, so we're going to end up with a square wave, looks like that. Okay, so when we find the Fourier transform of this triangular wave, now we've seen that in just the last video. Okay, now it ends up, it's a sinc squared function, so it looks something like that. Okay, now whenever we find the Fourier transform, what we do is we take the function f of j omega, so that's our sinc squared function, and we multiply it by j omega. Now in n this case will be 1, we're only doing one differentiation, so we multiply it by j omega. So what happens when we multiply it by j omega? Well, let's multiply it by omega first. Okay, so this is this function multiplied by omega. So omega, we have a value here, omega, it's always positive, so we multiply these by this value here, we're always going to get a positive value, so we're going to get something similar to this but just a bit bigger. Okay, so it'll look the same as that. Okay, but it'll just be the height of these will be higher. Okay, now and obviously actually, and the previous one here as well, when you get closer to 0, this, if I maybe fix that a little bit because it's not quite as straightforward as that, I'll redraw that. Say that again. So we're multiplying by omega, and when we get to 0, that will tend towards 0. Okay, so we'll get something that tends towards this here. Okay, something that looks like that. And in the negative side here, we're going to be taking this value here, but we're going to be multiplying it by negative, so negative omega, so it's going to take these and it's going to shift them down in the axis, and again when we get close to 0 we'll actually get that effect here, so we'll get something that looks like that. So that's us multiplied by our omega, and then we'll take that function there that will multiply by omega, okay, and then we'll multiply it by j. Now when we multiply it by j, it's equivalent to taking that function and shifting it by 90 degrees. Okay, so we'll get something that, again, it looks like what we've got above, but it's shifted on the axis, onto an imaginary axis by 90 degrees. Okay, so it looks something like this. So this is sitting in that plane there, but this one here is sitting in the imaginary plane. Okay, so we're going to have a purely imaginary function. Okay, so that's what we're going to get there. Okay, right, so that's all there is to this video, and next video we'll look at integration. Okay, thank you, goodbye.